Hello everyone. In this video, we're going to go over Chapter 5. This is a really big chapter. This is the first time we introduce hypothesis testing with effect sizes and confidence intervals. So what we want to do in this video is go over the essentials that you need to know in order to do the activities. So our goal is going to be to apply these 4 pillars of scientific reasoning to a specific research study or to a specific research context. So whenever we're trying to make conclusions about a given study regarding statistical evidence, we need to consider both statistical evidence and the scientific context, because research and statistics don't occur in a vacuum. You don't think about just one study by itself, nor can you look at statistics without understanding the quality of the research that was used to generate the data that you're analyzing. So in terms of statistical evidence, this is what we're going to be focusing most of our energy on because this is for a statistics class. So we're going to look at 3 different kinds of statistical evidence. We're going to look at hypothesis testing with continuous p-values. Our second pillar we're going to look at is practical importance with effect sizes. And our third pillar is population estimation with confidence intervals. So those form the basis of the statistical evidence for any given claim. What we also need to consider is the scientific context, and that's considering pillar 4 here, which is research methodology, and that's the quality of the study. Was it a well-done study? And also the scientific literature. How does this particular study fit into the given scientific knowledge that we already have? Okay. So we're focusing our energies on pillars 1 through 3. But if you've already taken research methods, you'll probably have a lot more to think about with pillar 4 as you work through the problems here. We're going to work through these 4 pillars of scientific reasoning with a particular example. So we're going to go through these pillars in order. The research question we're going to work with here is, can drivers accurately estimate the length of dashed lines on the road? So all of the dashed lines on roads in the United States are the same length. That's supposed to help drivers judge speed and distance between cars and between things. And so a student surveys a group of 49 experienced drivers, asking them how long they think the dashed lines are on the highway. And the student knows that previous research has shown that people tend to misestimate the size of objects, lengths of objects, distance of objects and lines. So the student expects experienced drivers will misestimate the length of dashed lines on the highway, despite the fact that they have a lot of experience with those very lines. So we want you to use the 4 pillars of scientific reasoning to determine if people can accurately estimate the length of lines. We're going to compare the sample mean of people's estimated dashed line length to the actual length of the dashed lines in the United States. So before we move on, think for a minute, what do you think the actual length of lines is? So take a second, pause the video if you need to. Okay, so the actual length of lines is 10 feet long. Right, so this is the value we're going to compare our sample mean to. Right, we're going to compare our estimates, or the sample estimates, to the actual length, which is 10 feet long. I know 10 feet seems wrong, but I promise you that is correct. We're going to start with pillar 1, looking at hypothesis testing with continuous p-values. There are quite a few steps to hypothesis testing, and most of them are new to you, and so we're going to spend quite a bit of time on this step walking through the mechanics and understanding what you're doing each step of the way here. So basically there are 5 steps we're going to follow through when we're looking at hypothesis testing with the continuous p-value. For this example, we're going to have a sample mean based on what people think the length of the dashed lines are, and then we're going to compare that sample mean to a value of theoretical interest. So because we're comparing one sample mean, and we have a sample mean because we're measuring length of lines of the road on an interval ratio scale, we can compute a mean of that. Then we're going to compare that mean to that value of theoretical interest, which is 10. We don't have a population mean or standard deviation, but we can compare that sample mean to that value of 10 with a t because it doesn't require population data. So the single sample t is our correct choice here. The second step is to look at the statistical assumptions. All statistical tests have assumptions to them, and if these assumptions are violated, the results of the test might be misleading. And so we have to be really careful to make sure that our given statistic and our study meet these assumptions. And there are 4 assumptions we're going to look at: independence, appropriate measurement, normality of distributions, and homogeneity of variance. Let's start with the independence assumption. So this assumption means that each participant's score within conditions is independent of all other participant scores within that same condition. What this basically means is that when people are asked, how long do you think the dashed lines are in the road, those answers need to be independent of everybody else in the study or in that condition. In this case, there's only one condition, so it's in that study. And so they can't look at each other's answers or talk to each other or cheat off each other. Everybody's answers need to be independent of everyone else's. Our next assumption is appropriate measurement. So for a single sample T, we have to identify a population, or we take a sample from that population, and then measure a variable of interest on an interval or ratio scale. And in this particular case, that means that we have identified this group of experienced drivers, taken a sample of 49 of them, and then measured how long they think the length of the dashed lines are as an interval ratio scale, because length of lines would be interval ratio. Our next assumption is normality of distributions. And this assumption states that the distribution of sample means must be normally distributed. This is often confusing because people want to look at the individual scores from their data set and assume that those need to be normally distributed, and that's not what the assumption is. It's that the distribution of sample means must be normally distributed. Now, luckily we know that according to the central limit theorem, the distribution of sample means will be normally distributed as long as your population of scores is normally distributed or your sample size is close to 30 or higher. So in this case, we have a sample size of 49, and so we should be very confident that our distribution of sample means will be normally distributed. Our last assumption is homogeneity of variance, and this means that the sample standard deviation is similar to the population standard deviation. This is hard to assess because you don't know the population standard deviation, and in the world of research, when people are doing this, what they wonder about is whether or not if they're using a manipulation of some sort, whether or not that manipulation is going to change variability in the scores. In this study, we're not doing any manipulating. We're just asking people how long they think the length of the lines are. So we don't think that the variability in the data set is going to change at all. Right? In this class, we're not going to try to trick you or give you examples where these assumptions aren't met, but what we want you to know is what the assumptions are so that when you leave this class and need to look at a new novel study with data that you've never seen before, that you know to look at these assumptions and make sure they're met and consider these ideas before you start analyzing your data. For step 3, we need to identify the null hypothesis. The null hypothesis states what the population parameters would be if there were no effect at all in the population. So for this example, what we're looking at is individuals in our sample and their estimates of the length of dashed lines in the road. Right? And we're going to compare their estimate to 10 feet. And so what we would expect, if there's no effect and people are really actually able to accurately estimate this line, that their mean should be equal to 10 feet. Now, when we write this out in population parameters in the symbolic notation, we're not making an estimate about our sample, right? We're trying to doing inferential statistics and make an inference to the population. So our null hypothesis is that our mean in the population is actually equal to 10. Or another way of writing that is that our mean minus 10 would equal to 0. Right? We're doing what is called a two-tailed test here because we're interested in results in either direction. Right? It could be interesting to find out that people underestimate the length of the lines of the road, or it could be interesting to find out that they overestimate the length of the lines in the road. Right? Sometimes people have a very specific prediction and they're only interested in results in one direction, like they're only interested in finding out if scores go up after a particular treatment. And if that's the case, they might do a one-tailed test. We're going to save that for a different video. This whole video is focused on a two-tailed test. The graph on the right is a box plot. So when you look at the box plot, you can see there's one line drawn through the middle of the box, and that is the median for the set of data. So you can see here that our median is a little bit over 8. The whiskers of the plot go to the lowest possible score in the data set and the highest score in the data set. The lines at the top and bottom of the box indicate the quartiles. So this bottom line is the score that represents the 25th percentile. The top line is the score that represents the 75th percentile. Right? So if you have outliers or problems with your data set, you can also see them in box plots before you start analyzing your data. Your next step, step 5, is to compute a t and a p. Right? We're doing a single sample t, and when we do a single sample t, we're going to get a p with it as well. So I used Jamovi to generate this output. But if you use different software, you'll have a slightly different looking output. I'm not showing you in this video how to run the analysis. That's going to be in a separate video. We just want to walk through the logic and mechanics of interpreting this. Right. So we have two different sets of output here. One is a set of descriptive statistics, and then another output for the single sample t-test. Right. So first you can see that we have an N of 49 people, right, who responded to the survey. We have a mean of 8.59. The standard error of the mean is 0.54. The median for our data set is 9. Our standard deviation is 3.7965. This is the standard deviation of the scores, right? Whereas the standard deviation of the mean is the standard deviation of the distribution of sample means, right? So 0.54 is the typical distance you would expect between sample means and the population mean if the null hypothesis is true. The standard deviation is the typical distance between scores and that sample mean of 8.59. Right, the lowest score in our data set was 1 and the highest was 15. Right. Now these data are used then to compute the single sample t. So I have the formula over here for the single sample t, and it is the sample mean minus the population mean divided by the estimated standard error. Right. So we're comparing our sample mean, 8.592, to 10. Right. So I know the formula says population mean, but that value could just be a value of theoretical interest. In this case, 10 is our value of theoretical interest. And then we're dividing by the standard error, right, which is the standard deviation divided by the square root of n. Right. So in your output, you'll see that you actually have all of these values. You have a mean difference of negative 1.408 down here, and you also have the standard error of 0.542 over here. And the mean and standard deviation are described over here as well, right, which gives us an overall t of negative 2.596. And you can see that there in the bottom output. Right. All right, so you don't have to do a lot of computations when you're using statistical software, but it's really important to know where the numbers are coming from with this t statistic. So take a moment to look over those, and then we can look at the p-value. Next, we need to look at our p-value. So the p-value is listed here in the bottom output. We have a p of 0.012 when our t is negative 2.596. And what we want to find out is what is the probability of obtaining a t of 2.596 or more extreme if in fact the null hypothesis is true. Right? So this distribution we've drawn here is a distribution of sample means assuming the null hypothesis is true and you have a sample size of 49. So if I were to take a sample from this population with a size of 49, I would expect to get a t that's greater than 2.596 or less than 2.596, 0.012 or 1.2% of the time. Right? So this gives you some hints as to why we call it a two-tailed test here, is because we're shading in both sides of the distribution. I know we computed a negative 2.596, but what we're interested in is whether or the likelihood of getting an outcome that extreme if the null hypothesis is true. And this suggests that this is a very unlikely outcome if the null is true, to just randomly pull a sample of 49 people and get a t out in one of these tails. Right. So the p of 0.02 here, right, that's a low p-value. It suggests that this outcome is really unlikely to occur if the null is true, and in fact, people can accurately estimate the length of the lines on the road, or actually know the length of the lines on the road. So this is very strong evidence against the null hypothesis. This is an unlikely outcome, which gives us strong evidence against the null. And because of this, then we conclude that people are underestimating the length of dashed lines, right? The sample mean was lower than 10. And that difference that we're observing is unlikely to be due to sampling error. It seems like people are really misjudging it, and they're biased in a way that makes us underestimate the length of those lines. Right? So when you're interpreting p-values, we want to think of them as continuous values that range between 0 and 1. Right? The lower they are, the closer they are to 0, the stronger the evidence is against the null hypothesis. And we have some guidelines here for interpreting p-values to get you started in thinking about this. The key to remember here is that our p-value really is a continuous value, and there's nothing magical about one particular cutoff value or another, just that lower values are stronger evidence against the null. So if you have like a p-value of 0.1, we say that's pretty weak evidence against the null hypothesis. If it's 0.05, that's moderate evidence against the null. 0.01 is strong evidence against the null. And then finally, the data are consistent with the null if your p is around 0.2 or greater. Right? So again, these are just guidelines. They're not hard and fast rules. We want to use p-values as a way to think about your data. This isn't a hard and fast rule, a cutoff that you just follow blindly, right? You're using this as a tool to help you think about your data. Don't use p-values as a substitute for thinking about your data. Okay, so that was all pillar 1. That was all hypothesis testing with continuous p-values. Our next pillar, pillar 2, is assessing practical importance with effect sizes. So p-values tell us if the results that were observed are likely to be due to sampling error, right? But we have other questions we want to ask about our data as well, not just are the results likely to be due to sampling error. We also want to know things about, like, are the results large enough or big enough to have actual practical importance? And there are two different ways we can look at effect size here. One, we can look at the raw scores. Another is we can look at standardized scores. We're going to start by looking at raw scores here. Like, we can just look at the mean difference in raw score units. And in this study, we can see that the mean difference was 8.592 minus 10, or negative 1.408 feet. So people underestimated the actual length of the lines on the road by 1.4 feet. Right? So that's one measure of effect size. This is how far we're off, right? We're off by 1.4 feet there. So in this case, our effect size was negative 0.37, which would be between a small and medium effect. Small to medium. And note, we're ignoring the negative side. Negative doesn't mean anything in terms of the size of the effect. That's just telling you about the direction of the effect. So we have a small to medium effect here. Right, moving along to our third pillar. Our third pillar is population estimation with confidence intervals. So far we know our p-value tells us the probability that we get these results because of sampling error. The effect size gives us an estimate of the size of the difference. Now we also want to know how confident we should be in our estimates of the population parameters. So your sample mean gives you one estimate of the actual difference between people's estimates of the lengths of lines and 10, right, in the population. And we want to know how precise that estimate is of that population mean difference, or that population parameter, that mean difference in the population. So to determine that, we're going to compute a confidence interval. So first of all, you're going to get the confidence interval in your statistical output. In this case, in Jamovi, we have the mean difference listed here, which is our point estimate. And then it gives us the lower and upper bounds, right? It's also going to give us confidence intervals around D, but we'll come back to those in a moment, right? So the way that Jamovi gets this answer is it computes the point estimate. and adds and subtracts the margin of error to that point estimate to get the confidence interval. Right? We're working with a 95% confidence interval, and so the T for the confidence interval, you can get, if you're computing this by hand, you can get it from the calculator on the textbook website, or you can also get it from a table where you would look up an alpha of 0.05 two-tailed with the degrees of freedom. The degrees of freedom for this test are n-1, so we had 49 people, so n-1 would be 48, and you would use this value here, the 2.0106, which is the same as you get with the calculator. Okay? Once you're using software to analyze data, you rarely have to compute confidence intervals by hand, but it's useful to know where the numbers are coming from. So this slide here shows you the point estimate is the mean difference. And then we compute a margin of error around that mean difference, and we get a margin of error of 1.09. So our upper bound is computed by taking the point estimate and adding the margin of error. The lower bound is computed by taking the point estimate and subtracting the margin of error. So this is a 95% confidence interval, and I can be 95% sure that the true mean difference in the population is somewhere between negative 0.318 and negative 0.2498. You're often going to find confidence intervals that are extraordinarily wide. When you find really wide confidence intervals, that's because the sample size for the study was just too small and it needs to be replicated with a larger sample size. You can also obtain confidence intervals around your effect size D. And this is, I have the output here listed from Jamovi. You can get it in JASP and some other programs as well. But note here that you can't do this by hand. Right? You need to get it from output. So in this case, our effect size range, our lower bound is negative 0.66 with an upper bound of negative 0.08. Right, so I'm 95% sure that the true mean difference effect size in the population is somewhere between very small to medium large. Right, that's suggesting a really wide confidence interval. And if you want a narrower estimate of the effect size, you want to be more precise, you need a bigger sample size. Okay. So note here that our negative sign again just means that the sample mean was lower than 10. It does not tell us how big the size is. You look at the absolute value of D to determine how big that effect is. Right? We already established that that was a small to medium effect that we're looking at there. All right, so now we've worked through the 3 pillars of statistical evidence. We have pillar 1, 2, and 3. We've worked through p-values, practical importance, and effect sizes. And now we want to at least acknowledge research methodology and scientific literature and try to put this study into context. In this case, we didn't give you a lot of information about the methodological rigor of the study. That you're going to find that often in the class. This isn't a research methods class, and we're not spending a lot of time on methodological rigor, but sometimes we will. Sometimes we'll talk about very specific things that might have gone wrong in a study. Right? In this case, there's nothing obvious that went wrong by asking people how long they think dashed roads on the line or dashed lines on the road are. Our next one is determining how well the study fits into the scientific literature. What we did in the original slides early on say that previous research has suggested people aren't good at estimating size and length, and so our results seem to be consistent with that. And people weren't great at judging size and length here, or length here, when we're looking at the length of the lines on the road. Right? So it seems to fit in with what we already know. We don't know a lot about methodological rigor of the study, but we want to think about it when we can. All right, finally, once you have done all of this, we need to pull it all together in one well-supported scientific conclusion. And in our scientific conclusion, we want to talk about all 3 pillars of statistical evidence and also discuss, to the extent possible, pillar 4, the scientific context. So you want to start with an APA-style summary of the results. This is a very specific reporting format that people use across disciplines. Some disciplines have slightly different reporting, but you'll find them all very, very similar. This makes it way easier to read journal articles if everybody's reporting the results in a very regimented, sort of similar fashion. Right? So the way we report this is we say which statistic we computed. Right? We computed a single sample t-test and an effect size to compare the average estimated length of dashed lines on the road. And here I'm giving my sample mean and standard deviation. This came from that original descriptive statistics table. Right? So I don't have that replicated here, but it's in a previous slide where you can look at the mean and standard deviation there. And you can compare that mean to the actual length of the lines, which is 10 feet. Then after this, we have a giant string of numbers, and so let's go through what all these numbers are. The first number in parentheses here is the degrees of freedom for the test, which is n-1, and all these numbers are listed in the output below. Then you have the t that we computed is negative 2.60. Notice that I've rounded to 2 decimals because that's APA style. We report to the second decimal place. Our p is 0.01. Our 95% confidence interval around the mean difference is negative 2.5 and negative 0.32. Our effect size D is negative 0.38, and the confidence interval around that effect size is negative 0.66 to negative 0.08. Note that it's lower bound first and then the upper bound. Right? So that is just a summary of your results with no interpretation at the moment. So after you summarize the results, you next consider the research methodology and the scientific context that you're working with. So in this case, our study, we're saying, is consistent with the previous research, showing that people don't accurately estimate the lengths of line or size of objects in research. And I'm just saying that there are no obvious methodological problems with the study, but we do know that our confidence interval was very wide, right, around that effect size. We were pretty sure that the effect size was between kind of small and large, or almost large. So if we want more precise estimates, we should replicate the study with a larger sample size. Right? Note that we don't always in class examples give you a lot of information about the scientific methodology or the previous research. If that's the case, just say that you don't have enough information about scientific research or research methodology. But including it sort of as a placeholder in your summary is important, so once you take a research methods class or have more information about it, you remember to talk about your results in this broader context, not as a standalone concept. All right, so now we're going to pull everything together into a final scientific conclusion. I'm starting with that APA style summary of the results. And then you'll note here that I added at the very end of that first paragraph a statement that people underestimated the length of the lines by 1.41 feet. Right? Just to provide a little bit of context so readers don't have to do that subtracting in their head. We already provided an effect size D in standardized units, but it's useful to see the raw score units here as well. And then the next paragraph we have here is relating our results back to the original scientific literature and also talking about any methodological issues with this study. So in terms of previous research, we had cited at the beginning some previous research showing that people do not accurately estimate the length of lines. And so we just state that our results are consistent with that existing research, which makes us more confident in them to the extent that they fit with what we already know about this area. And then we don't know of any obvious methodological problems with the study. However, we are aware that our estimates of the population parameters are not great, right? Because our confidence intervals are pretty wide, right? We think that our effect size is varying between medium to large to basically 0, right? So if we want more precise estimates, we should really replicate that study with a larger sample size. So people's inclination is always to say at the end, well, you should replicate it with a bigger sample size. I agree that you should always replicate studies, but a bigger sample size isn't always necessary. Sometimes the original study had a fine sample size. You just need to look at the data closely to make that sort of determination. Finally, I just wanted to provide the references that we cited early on in the slides. And also note that I made up the data for this example. This isn't data that we actually obtained. I would encourage you to ask some of your friends, ask classmates what they think the actual length of the lines are. People generally underestimate by way more than I suggested in this example. People often think that the actual length of the lines is more like 2 feet, which is really problematic. The only reason that I didn't use data like that for this example is because if I use that, you end up with these crazy large T's and very low p-values and giant D's that you really rarely see in typical research. So just to be aware that our data is consistent in terms of we find that people underestimate, but people underestimate by a much larger amount than this little example suggested. Okay, I hope this helps. So although this was, it feels like a long video, it was 30 minutes, but it's still a pretty quick introduction to all of hypothesis testing. And we skipped some things in the chapters about sort of controversies in the field, about p-values and things like that. So there'll be other videos on the website to take a look at for a little bit more in-depth treatment of particular topics there. But this is definitely enough to get you going and started on the activities in the chapter. All right, good luck.